Okay, everybody. So to take my lessons with derivatives, rates of change, instantaneous rates of change, average rates of change, Leibniz notation, to take that one step further, I want to do another problem where I think it's easy for you to imagine. Okay? So here's the idea. This is not some exotic situation that you can't think about or you can't get a mental image of. If I say that we have a pulley on a dock, the pulley has a rope wound around it. The rope's attached to a boat. The boat's on the water. The dock's 3 feet above the water. Okay? So, all right, we're pulling the boat in towards the dock by way of the rope and the pulley. And the boat moves on the water. Okay, so that's not too hard to understand. So, where's calculus come in? All right, well, here's what I'm curious about. Let's suppose that, just for the sake of example, we reel in the rope 1 foot, total distance. Okay? So the rope's so many feet, we reel it in and it's 1 foot shorter. So we pull in 1 foot of rope. How far will the boat move on the water? Now I hope that this sounds like other problems I've been doing, like my earlier videos were that, well, if you have a situation and there's variables, the variables will change. If they don't change, then they're constants, okay? And if they change, then probably change in one causes change in the other. So if I say, all right, the distance on the water that the boat is from the dock, let's call that x, and then the length of the rope, we'll call that r. So if r gets shorter by action of pulling in the rope, x will get shorter. But will they get shorter in the same way? Okay? How does r getting shorter cause x to get shorter? Like if I reel in 1 foot of rope, does that mean the boat moves exactly 1 foot on the water? Or does it move more or does it move less? Okay? Now, try to get your instinct. What does your instinct tell you? If we pull in 1 foot of rope, does the boat move 1 foot on the water? So if we pull in 1 foot this way, then the boat will move like this. That's just how it is. But does it also move a foot? What does your instinct tell you about that? Does it move a little bit more? Do you think it'll move less? Okay. If you have some instinct, or if you at least think about that question, maybe you're like, I don't know. But at least if you think about it, I think the math will make a little more sense. So in order to address this, I'll ask you to do this problem. Can you calculate delta x? Okay, so that's the change in this side of this triangle. Okay, it getting shorter as you pull the rope in. Calculate delta x over delta r. That's the average rate of change of x with respect to r. If r is 75 feet, so you've got 75 feet of rope, and delta r is 1. Pull in 1 foot of rope. Okay? And technically, if delta r is positive, we'll add to it. But, we can, whether we add or subtract, we'll get to explore it either way. Okay? All right. So we'll do that one. And then I want to do this other one. What's delta x over delta r if r is 20 feet and delta r is 1? Okay. Now, why do both if I say, well, so the rope changes by a foot, in either one? Why did I do both of them? Well, because, if the rope changes by a foot, actually what happens is how much it moves on the water it's going to depend on how far away it is. Okay. So that's why I want to do both. Here, this is farther away. And here, this is closer. And you can pull in a foot of rope or have the rope length changed by 1 in either case. But the distance the boat moves on the water is going to be different depending on if it's further or closer. All right? Okay, so let's do both of these. And we'll compare the answers. So, all right, if we're going to do this, what do we need to start with? How do you calculate these changes? One way to do it, actually, I don't normally mention this because it's not of great importance in our class. Our class doesn't have a laboratory component, but you could measure it if you want to. Like, if you drew a scale drawing and you say, okay, I got the rope there, and I'll measure like a 1 foot less or 1 foot more of rope, and then I'll measure, I'll replot it, and then I'll measure the distance on the water, all according to my scale picture. I could do it like that. I mean, that would be measuring the change in this side versus the change in this one, okay? But like I said, that's, you try that if you want to. Your picture's got to be to scale, and you got to choose some kind of measurement that is accessible on your measuring device, whatever it is, okay? So you could do that, but what for us, for our class, given that we'll learn to do math on paper, is we need a function. I need x to be a function of r if I'm going to calculate these, okay? So you might think, is there some equation by which x and r are connected, like that if you knew one, you could find the other? Does such an equation exist? Well, as we look at this, it's, I've constructed it that the pier on the dock is roughly perpendicular to the water, and the water's not too turbulent, and so we'll represent by a straight line, and the rope doesn't have any slack in it, so we'll represent it by a straight line. So I've done all that. It's a right triangle. So yes, there is an equation that relates this and that. You need to know this side too, though, and that's the Pythagorean theorem. X squared plus 3 squared is equal to r squared. Okay, so that equation would be applicable. So we can do this if we wanted to solve for x. That puts x to be a function of r. You plug r, the length of the rope, in, you calculate x, right? All right, so that's our function. Now, what are we doing? So delta x over delta r, if r is either 75 or 20, and delta r is 1. So here you're looking at it. 75 to 76. Delta r is 1 right there. Calculate x this way. Okay, delta x over delta r is this minus this over this minus this, okay? And that will be about 1.00079, okay? Now, is it just a number, or does the number mean something? I was exploring this to give you a way to answer this question of, is a foot of rope worth exactly 1 foot of distance on the water? Well, it turns out no. Remember, what's x? X is the distance on the water. What's that in? Feet. So that number up there has units. It's feet. What's this 1, delta r? That's change in the length of rope. How do you measure that? Also feet. So we could say that this is 1.00079 feet per foot. Or 1 foot of rope is worth a little more than a foot on the water. Okay? All right, so now you find the deltas, you get a number, but you can think about what the number means. Okay, so will it move a foot? Well, actually a little bit more. If you pull in a foot of rope, or if the rope length changes by a foot, it'll move on the water a little bit more than that. Now that's when it's, I guess, fairly far away, 75 feet. What about this other one? What about when the rope is 20 feet? That'll put the boat closer. What's different about it? Well, okay, so it's a 20 to 21. There's the x for each of them. There's delta x over delta r. And again, this is in feet. These numbers are in feet, they're distances. That number's in foot. And so this is 1.011 feet per foot. So, all right, I could give the same interpretation to this number. 1 foot of rope, when it's 20 feet, is going to get you a little bit more distance on the water. That is more than this. You might say, well, it's not much more. It's not worth arguing about. But it's as the boat's closer, it's going to move further on the water than every unit of rope that's pulled in. Okay, that's what that says. All right. Okay, 1.011 being a little bit bigger than 1.00079. So, all right, I got both of those, and I think they do shed some light on this, that it's not 1. It's not exactly 1 to 1. It's 1 to a little bit bigger number than 1. Okay, 1 foot of rope means something a little bit more than 1 foot on the water. And it'll move further on the water the closer it gets.